Hi guys, this is Mr. Pinter. Welcome back to our last part of Chapter 4 video on the continuous time Fourier transform. In this part of the lecture, we will be doing system analysis using Fourier transform methods. The first thing we're going to do is show a way to find the system output by using the frequency response. So this is one of the important applications of the convolution property of the Fourier transform, is that we can find the output of a system. So if we are given an input signal x of t, and we're also given the system's impulse response h of t, we are often tasked with trying to find the output of the system. What does the system do in this case? So we want to find y of t. So we learned back in Chapter 2 that usually, the hard way to do this is by using convolution. So working in the time domain, the only way to figure out the output here, y of t, is to take the convolution of x and h. And remember, that's what this symbol here means. This is the convolution operator. And so this convolution is performed by using the convolution integral here. And you'll remember, of course, from Chapter 2 that this is often very difficult and tedious work to figure out the convolution here. So what we can do now is something a lot easier usually, and it's sort of a nifty trick using Fourier transforms in the frequency domain, and we can avoid convolution altogether. So the idea here is instead of working with x of t, we're going to work with x of j omega. That is the Fourier transform of the input signal. And instead of working with h of t here, the impulse response, we're going to work with the Fourier transform h of j omega. And remember, h of j omega is called the frequency response, and it's the Fourier transform of h of t. So in the frequency domain, what we have is, the input signal x goes into our system. The system has a frequency response of h, and the output y is given by the product, not the convolution, but the product of x and h. So this is, the advantage of working in the frequency domain. We don't have to do any convolution. We can just multiply these two functions together. Now, there's no free lunch here. We still obviously have to do Fourier transforms to work in the frequency response, but a lot of times this is much easier than, certainly easier than doing a convolution up here. And then once we get this Fourier transform of the output here, big Y of j omega, we have to still figure out what is y of t, and we can do that by finding the inverse Fourier transform of y. And we can either do that, using the formal method is with the inverse Fourier transform integral, or a lot of times, in fact, all we're going to do in this course is just do it by inspection using basically Fourier transform pairs that we have already determined previously. So we'll see some examples of this coming up real shortly. So here's our first example of finding the system output. So suppose we're told that we have an LTI system, and the input of the system, x of t, is an exponential function e to the minus bt times a step function, u of t, and b is some positive number. And also the system has an impulse response which is given to us, and it is also an exponential function, e to the minus at times a step function, u of t. And in this case, a and b are assumed to be different numbers. So this is what, if we were to plot the input, that would be in blue. And if we were to plot the impulse response, that would be in red. So that's blue is x and red is h. And our goal is to find the output of the system here. All right, so obviously, again, we could do this in the time domain, but we'd have to do a convolution of these two signals here. So instead, we're going to work in the frequency domain. And so the first thing we need to do is we need to find the Fourier transform of x and the Fourier transform of h. So the good news here is we already learned earlier, it's not slide 7, sorry, but earlier in this chapter, we found the Fourier transform for a exponential function, and it is shown right here. So in this case, our Fourier transform of x, looking up here, notice the number in front of the t there is b. All right, we're not told what b is, but it's just a positive number. So using this Fourier transform pair, we can see that the Fourier transform of x is just 1 over b plus j omega. So this is nothing new. We've done several examples like this so far in this chapter. And likewise, we can do the same thing and find the frequency response h just by using this result from earlier in the chapter. So h looks just like x, but the difference is here we have an a up here in the exponent, not a b. So there's the a down here. So using the convolution property, remember the output here of this system is just the product of the Fourier transform of x and the frequency response h. So we just take these two functions here and we just simply multiply them together to get this form right here. So at this point, this is the output of the system, but this is the output in the frequency domain. This is the Fourier transform of the output. So we want to find y of t, go back to the time domain. So to do that, we have to use an inverse Fourier transform of this here. Now, unfortunately, we don't have a result that looks like this. We have this guy up here, which looks like part of it, but not the product of the two of them together. So the two ways to proceed here is you could try to use the inverse Fourier transform integral, but that would actually be kind of a mess. So the easiest way to do this is by using a clever trick called partial fraction expansion. So let's take a look at what partial fraction expansion is. You've probably seen this before in one of your math classes. This is a trick that's often used to expand a fraction that looks, something like this, that's got, a product of terms in the denominator. We can break it apart into two pieces. So the idea here in why we're going to do this is because when we break this thing apart into two pieces, we can do the inverse Fourier transform of each of these pieces just by inspection. We know how to do this term and we know how to do this term. We just don't know how to do the two terms multiplied together. So notice what you do here is, we've got these two in the denominator. We've got the two terms down here, a plus j omega multiplied plus b plus j omega. And so here we break this thing up into two terms. The first one has an a plus j omega and the second one has a b plus j omega. And then we put a couple of constants up here. You can call them whatever you want. You can call them C1 and C2. I called them uppercase A and uppercase B. And of course, these constants at this point are unknown. So the task for partial fraction expansion is to determine what these partial fraction expansion coefficients are. And again, if you look this up in a textbook or just look it up online on how to do partial fractions, there are various methods that you can use to find A and B, but by far, to me, the most quick and easy method to find A and B is the following. Let's say we want to first determine what A is here. So what we do is, to solve for A, we got to get rid of this A plus j omega on the bottom. So we're going to multiply everything, the left side and everything on the right, by A plus j omega. And let's see what happens here. So when we multiply this side over here, multiplied by, this term, A plus j omega, small a plus j omega, notice it cancels out this term over here. And you'll always have some sort of canceling like this. This is what makes this very easy. So on the left, we just have 1 over b plus j omega. And on the right, this term, this big A here becomes all by itself, isolated, right? Because we're multiplying through by A plus j omega. And the second term, becomes a little more messy. We've got the uppercase B times A plus j omega divided by B plus j omega. Now, the trick here, though, and this makes this very easy, is that this expression here has to work for all values of omega. So what we can do is choose j omega such that it's equal to negative a. And watch what happens here. Now, why did I choose negative a? We want this term here to go to 0. because if this term goes to 0, then my a here is all by itself, and we've basically solved for a. So how do I make this term go to 0? Well, we want the numerator to be 0. So the numerator will be 0 only when j omega, remember omega is like a variable, it can be anything. J omega we can set to the opposite of this little a right here. So that's why I'm setting j omega equal negative a. And when I do that, this second term here just magically disappears. And all we have to do down here, remember that this j omega now becomes negative a again, right? We have to, if we set j omega equal to negative a over here, we have to set j omega equal to negative a on the left side. So the left side just becomes 1 over b minus a. And then the right side, of course, we have solved for uppercase a, and there is our result. So depending on what these numbers are, b and a, this will give us the coefficient of the partial fraction expansion, the coefficient uppercase a. And then we can go back to this and we can repeat the process to find what uppercase b is. So to find what uppercase b is, we're going to multiply it first every term by little b plus j omega. Okay, and so when I do that over here on the left side, notice it's going to cancel out this b plus j omega on the bottom. And that's going to give us this, 1 over little a plus j omega. On the right side, this term here, the first term, is going to pick up that b plus j omega term, and then of course the second term on the right is going to be the uppercase b all by itself, which is what we want to do. Now again, we use the same trick. We want to get rid of this first term here so that b is isolated and all by itself. So to do that, we just simply set j omega equal to negative little b, lowercase b. All right, so down here on the left side, we have 1 over a minus b, all right, that's shown here. And then, of course, this term goes to 0 when we set j omega equal negative b, and so we end up with just b by itself on the right, and here is our result for uppercase b. Notice it looks just like uppercase a's results, except the bottom terms are flipped. Here it's b minus a, here it's a minus b. If you're rusty on partial fraction expansion, you can look it up online and review this on your own. This is a good tutorial that I found right here. There are certainly others that you can find as well that'll help you. If you're not sure how to do this, you'll need to look this up on your own and make sure you can master partial fractions. Okay, so we're not done yet, obviously. Now we can go back and we can replace uppercase a with this coefficient here, which we determined, and here's our result for uppercase b. And again, both of these coefficients are equal to each other. They differ by a minus sign. So let's pull out 1 over b minus a from both of these terms. And we end up with 1 over a plus j omega minus 1 over b plus j omega. Now, where did this minus sign come from? Well, remember that this term up here is the opposite of this coefficient here, because this one is b minus a, this one's a minus b. So this is just some simple algebra. At this point, we're not doing anything that difficult here. Just have to, be very careful that we don't flip a sign or forget a negative sign or something like that, because obviously then we're going to get the wrong answer. So now that we've got our output of our system, y of j omega, in this form, it looks kind of messy, but actually we know how to invert this by inspection. Because again, remember this result here that we learned earlier in this chapter. For exponential functions, this is what the Fourier transform looks like. And so both of these terms here are just exponential functions when we go back in time. So using this result here, just by inspection, we can see that here the exponent is going to be an a, and here the exponent is going to be a b. And so we get, now we've got our time result. The output of the system, y of t, is equal to 1 over b minus a, and then times the product, all in parentheses, of two exponential functions, e to the minus at times ut, minus e to the minus bt times u of t. And I can even factor out this step function and put it outside. So this is the final simplest form here. And if you were to plot this thing, depending on the values of a and b, remember a and b are just two positive numbers. This thing is going to look something like this. It's going to, the output of the system is going to rise up to some peak, and then it's going to basically, as time goes on, the output of the system is going to decay to 0. Now, there's one thing, more we can do here is verify these results using the convolution method. I'm not going to go through the details here. Personally, I don't enjoy doing convolutions, but I did work out the steps here. In fact, this is very similar. This problem is almost exactly similar to a homework problem that you did in Chapter 2. It was with, these same two exponential functions. I think instead of a and b, it used alpha and beta. So if you want to look back on that. But anyway, and we also did an example like this in Chapter 2. But these are the steps, using the convolution method between x and h. And, not surprisingly, when the dust settles here, we get the exact same result. So certainly, I would rather do the convolution in I'm sorry, not convolution. I would rather use Fourier transforms in the frequency domain and avoid doing convolutions. One of the other extremely important applications of Fourier transform methods is that we can solve differential equations. And the reason this is important for us in this course is remember that LTI systems in continuous time are usually described by linear differential equations. So, the linear differential equation is like a model that basically describes the behavior of the system. So, working with a linear differential equation that describes a system, we usually need to solve that equation to find the output of the system. And so here I'm going to show you, this is, pretty neat to be able to use Fourier transform methods to solve linear differential equations almost by simple inspection. So it's almost too good to be true. All right, so before we, I actually show you an example on how easy this is, I want to just kind of show you the theory and derive how we come up with these results so that you'll realize that it really isn't magic, it's just mathematics. So remember that LTI systems are often described by linear differential equations. So we saw examples earlier in the course, I believe it was back in Chapter 2, where an RLC circuit is always described by a differential equation, and also many mechanical systems, for example, those that have springs with friction. We saw the automobile suspension system and so forth. Those are also described by linear differential equations. So we're going to put the linear differential equation in this form here. So notice, y, remember y is the output of the system. So all the y terms are on the left, and x is the input to the system. So we're going to put all the terms with x over on the right. This is standard form. And I've put the I put y, by itself here first, and it has some coefficient a0, which may or may not be 1. And then this is the first derivative of y, with its coefficient a1. This is the second derivative of y with its coefficient a2, and so on and so forth. And then similarly, on the right side of the equation, I've grouped, I put the x here, and then the first derivative, and then if there are any higher derivatives, those would follow over here. So we're going to use the linear differential equation in this form here. So kind of skipping ahead here, and we're going to show how to do these steps, but the reason we're going to do this is that Fourier transform methods can be used to find the following. We can find the system's frequency response, all right, h of j omega. We know how important frequency response is for a system, and we're going to show a method where we can actually write the frequency response directly from this equation just by inspection without even having to do any math. All right, again, this almost seems like it's too good to be true, but this is one of the great powers of the Fourier transform and working in the frequency domain. we'll be able to, once we get that frequency response, we'll be able to invert that and find the impulse response and find out, is this system stable or unstable? And then our ultimate goal here is to solve this equation here, find the output y of t for any given system input x of t, which appears over here on the right side. And so let's, how do we do this? Well, what we're going to do is we're going to take the Fourier transform of the entire equation here, and we're going to do it term by term. So in other words, we're going to take the Fourier transform of this term first, and then we're going to add that to the Fourier transform of this term, and then add the next term, and just keep on going through the whole equation here. So let's see what happens when we do this. So first of all, our notation here is this first term, we've got a naught, which is just a coefficient, times the Fourier transform, that's what f means here, the Fourier transform of y by itself. The second term, we have a1 times the Fourier transform of dy dt, so that's the first time derivative. And then the second term, or I'm sorry, the third term is a2 times the Fourier transform of the second time derivative of y, and et cetera, et cetera. Okay, and then on the right side, likewise, we have b naught times the Fourier transform of x plus b1 times the Fourier transform of dx dt, which is the first derivative of x, and we would keep going if necessary. Okay, so at this point now, here's where the magic sort of appears. We're going to use the differentiation property. And remember, we learned this in one of the earlier parts of this chapter's video lecture. The differentiation property is extremely important, and because it replaces derivatives with just algebraic factors. So here's a summary if you've forgotten. The first derivative of a variable, in other words, dx dt, this is just the Laplace transform x multiplied by a factor of j omega. And the second time derivative of x is, again, just the same Fourier transform x multiplied by j omega squared. Okay, and so if you've forgotten where that came from, you might want to review that. That was earlier this chapter. We derived this differentiation property. So when we do this, look what happens. So here's our this is our term by term Fourier transform. This is just the same. This is from the bottom of the last slide. So now I'm going to apply the differentiation property and see what we get. So this first term is a naught, and of course when we take the Fourier transform of little y, we just get big Y. All right. The second term, we have a1, and this is the Fourier transform of dy dt. Now, remember, using this up here, this becomes we pick up a factor of j omega times big Y, times the Fourier transform of y. This term here, the third term, has an a2 out in front. It's a second derivative. Remember, a second derivative, we pick up a j omega squared. So we're going to have that out in front of the y, of the big Y. All right, and then we would keep going if necessary, if there are higher order derivatives. And then we do the same thing on the right side. First term becomes b naught times uppercase x. Second term, b1, we have a factor of j omega because this is a first derivative. And then dx dt just becomes the j omega multiplied by uppercase x, which is the Fourier transform of x. Okay, and then we keep going if necessary. Now, what we can do is, this looks like a mess, right? But we can simplify this substantially. Notice there are no more derivatives in here at all. This is just an algebraic expression, and notice every term on the left has an uppercase y, has big Y. So let's factor that out. So what's left? Well, we have all the coefficients, a naught plus a1 times j omega plus a2 times j omega squared, and we keep going if needed. On the right side, all the terms will have an uppercase x, so factor that out, and we have b naught plus b1 j omega plus b2 j omega squared, etc., etc. All right, we're almost there. Remember that the convolution property tells us that the output of a system in the frequency domain, all right, this is y of j omega, is equal to x of j omega times h of j omega. So in other words, let's solve for h of j omega. H of j omega, if we solve this equation right here for h, it's just y over x. So it's the Fourier transform of y, big Y, divided by the Fourier transform of x, big X. And we can get that from the stuff inside these parentheses here. All right, so when we take this equation here and we solve it for y over x, we get the following. We get all of the b coefficients, all right, which actually were here in front of x, divided by all the a coefficients, which are over here in front of the y. All right, so we've got b naught plus b1 j omega plus b2 j omega squared, and keep going as needed. On the bottom, we have a naught plus a1 j omega plus a2 j omega squared, etc., etc. One thing so what we're going to do is, the good news here is we're not going to have to go through all these steps every time. These coefficients here are just the coefficients in the differential equation. So we can actually write our frequency response by inspection without having to do any work at all, okay? One thing I will caution you here is, remember, frequency response is y over x. However, these coefficients on the top are the x coefficients, and the ones on the bottom are the y coefficients. Okay, so why are they opposite to here? Well, it's because when you divide to get y over x, you're dividing in the opposite order to move them to the other side. All right, if that's not real clear, this is just some simple algebra here. Okay, so but remember that these b coefficients here are not the y's. Notice the b's were the ones in front of the x's, and the a's were the ones in front of the y's. So let's do an example, and I'll show you how simple this actually is. All right, so here's our example of a Fourier transform method to solve a linear differential equation. So suppose that we're given an LTI system that's described by the following linear differential equation. We have second derivative of y plus 2 times derivative of y minus 8y equals dx dt minus 2x. So the first thing we're going to do is we're going to write the frequency response of this system by inspection. So how do I do that? Well, remember, on the top in the numerator, we have to use the x coefficients, okay? So all we have to do is remember that a first derivative gives us a factor of j omega. So I'm going to write down the j omega. And this is minus 2 here in front of the x, so we pick up our minus 2. Remember, the x is gone, right? We factored that out. It became the Fourier transform of x, which we factored. So all we're looking at here are these coefficients, all right? So the top is easy. We just look at this and we say j omega minus 2. On the bottom, we kind of do the same thing. We're going to, the denominator of the frequency response is going to be the y coefficients. So this is a second derivative of y. So remember, that gives us a factor of j omega squared. Here we have 2 times a first derivative of y. So that's going to give me 2 times j omega, the j omega from the derivative there. And then the minus 8y just gives me minus 8. So I can write this frequency response simply by looking at the coefficients in front of the derivatives, okay? And at this point now, we can go a little farther. We can factor the denominator here, okay? If you think of j omega kind of like x, then we have x squared plus 2x minus 8. And that factors as, x plus 4 times x minus 2. But remember, x is j omega. So you'll get used to factoring things in terms of j omega. It's just as easy. You just have to think of j omega as the variable. So this becomes factored j omega plus 4 times j omega minus 2. And the nice thing with this example is this top term cancels this term in the bottom. And we end up, here is our frequency response for this system. H of j omega is equal to 1 over j omega plus 4. Now from the frequency response, I can immediately write the impulse response. So in other words, I can go from big H to little h by using, again, here it is, over and over, we see this same Fourier transform pair for an exponential function. And so by inspection, we can see that A here is 4, okay? So this impulse response becomes e to the minus 4t times a step function u of t. And we can also tell just by looking at this impulse response, this is a decaying exponential function. So it's going to go to 0 as t gets large. So remember, that's by definition, that tells us that the system is stable because the impulse response decays to 0. Okay, now the next part is we want to find the output of the system. But in order to do that, of course, we need to know what's going into the system. So let's suppose we're given the input of the system is the following exponential function, e to the minus t times u of t. And so again, we're going to work in the frequency domain. So we're going to take the Fourier transform of x, and once again, here we're going to use the same Fourier transform pair. It keeps on showing up, I know, over and over, and the reason for that is that exponential functions like this solve differential equations. So these are very useful Fourier transform pairs to use. So anyway, just by inspection, I can see that this signal here for x of t has the following transform, x of j omega, because by inspection, it looks like a here is 1. There's a minus 1t, so that a is a 1, this a here is a 1, which gives us this form. And the output of our system, remember, big Y is equal to big X times big H. Don't need to do convolution, of course. We're just multiplying. So we're going to take our frequency response from the last slide, which was 1 over j omega plus 4, and we're going to multiply it by our Fourier transform of x, which is shown right here, 1 over j omega plus 1, and we get this form here. So this is the frequency response of the output of the system. Now this is just like the problem we did a few slides earlier. In order to invert this, we're going to do partial fraction expansion to break this fraction here up into these partial fractions here, right? So again, we split it up into the two pieces, call one uppercase A and the other is a coefficient uppercase B. And I'm not going to go through the details on how to find A and B, but remember we just did this a few slides ago. You just use the same method and you'll find out that, let's see, uppercase A, it looks like it turns out to be 1/3, and uppercase B turns out to be minus 1/3. That's why we pick up that minus sign there. So I can factor out that 1/3 out in front, and I end up with 1 over j omega plus 1 minus 1 over j omega plus 4, and then again using the same exponential function Fourier transform pair, by inspection I can see that this first term here has, little a is equal to 1. So that's going to give me e to the minus t. And the second term here, I can see that by inspection, a here is equal to 4. So that's going to give me e to the minus 4t. And then, of course, remember that minus sign in front there. That's the minus sign right here. And also there is a 1/3 out in front. And then don't forget also the step function here, which has both of them multiplied together. So there is our solution to that differential equation, and we did it without having to do any calculus. Here we just solved a second order linear differential equation that had derivatives and even second derivatives in it, and we didn't have to do any calculus. We just had to do some algebra. So this is again one of the powerful applications of Fourier transform methods in terms of solving something as complicated as a second order linear differential equation. We can solve it just by using some algebra. The last couple of examples here in this chapter, I'm going to just show you how we can also work backwards. We can start with a frequency response that's given to us, and we can write a differential equation that describes the system. So suppose instead of being given a differential equation, we're told that a system has the following frequency response. So h of j omega is equal to 2 j omega plus 1 over j omega squared minus 3 j omega minus 4, and we're asked to write the differential equation that describes this system. Well, all we have to do here is work backwards and use the same inspection method to write the differential equation. So what I'm going to do here is I'll start on the left here, which are the y terms. And remember, the y terms are defined by what's at the bottom here in the denominator. So j omega squared, that tells me I have a second derivative of y. So it's d squared y over dt squared. Then I have a minus 3. Here's our minus 3. And j omega tells me I have a first derivative of y. Remember, this is the differentiation property. And then minus 4 tells me I have a minus 4 times y. So that takes care of the left side. Now the right side are all the inputs, the x's. And so I'm going to use the top here of the frequency response to write the x terms over here. So the first thing I see is 2j omega. So I have my 2 here. Remember that j omega implies a first derivative. So I have dx dt. And then plus 1 here gives me plus x. So there it is. This is the differential equation that describes the system that has this frequency response. Here's one more example that's just a little different. This time, suppose the frequency response is given to us in this form, where the bottom is factored. Okay. Well, we don't know how to, work with this form by direct inspection. So the trick here is pretty simple. We just expand or FOIL out the denominator here. And so I have, j omega times j omega is j omega squared. And then I have 4j omega, that's the outside. The inside is minus 3j omega. So when I add those together, I get j omega. And then I have last terms, right, I'm doing the FOIL method. I have minus 3 times 4 gives me minus 12. So now that I have it in this form, I can again just go by inspection. On the left side, I see j omega squared. That's going to give me second derivative of y. Here I have j omega, which gives me dy dt. And then minus 12, I have minus 12y. And then on the top, I have j omega, which gives me the first derivative of x. And then minus 5 gives me 5x. And here is our differential equation. Okay, you guys, that is it for Chapter 4 on the Fourier transform. Everything we did in this chapter, you'll recall, was for continuous time systems. And so obviously we would like to do the same type of analysis with Fourier transforms for discrete time systems, and that is the subject of the next chapter. Chapter 5 is basically the exact same thing as Chapter 4, except we are going to work in discrete time instead of continuous time. So until then, I'll see you in Chapter 5. Take care and goodbye.